much of the machine learning aspect of fractional phases, and some of the work carried out with D. Law from recently joined UCLA, together with MIT student. Okay, so yeah.
Is it on?
So, yeah.
Very small, so it's like,
Okay, so as we know, the study of fractionalized phases, fractionalization phenomena started with the discovery of the fractional moire effect. This refers to two-dimensional electrical system of a strong magnetic field, and for several decades, this has been an enduring source of inspiration, giving rise to many theoretical ideas. And even though the direct evidence of fractional charge and fractional statistics came much later, the existence was widely accepted, and that was based on simply measuring the Hall effect. So as we know that at various filling fractions, at another level of filling fractions, the Hall effect is quantized into a fraction of U over Q, and whenever the Hall effect is quantized, it immediately implies the existence of quasi-particles carrying a fractional charge, which is 1 over Q, and this was established directly by a so-called Lawson argument. When you run a flux through an infinitesimally thin solenoid and turn on the flux, a flux from 0 to 1 plus quanta, then it induces by the law of electromagnetism, it induces a circulating electric field. And then through the Hall effect, it leads to a current in radial direction. And the net result is that you accumulate a charge, which is C over Q times electron charge E. And because one flux quanta can be H away, this implies that the system actually supports fractional charges P over Q. And further, you can combine this fractional charge with the integer charge, and that immediately leads to the result. There exists fractional charge, which is 1 over Q. And the theme of fractionalization has since then become much broader. And on the theoretical side, the theorists have shown that electron fractionalization also occurs in electron spin systems, magnets, fractional magnets, for example. And here, even when the charge diffusion freedom are frozen, we have a lattice with 1 electron every side. The spin diffusion freedom can be active in the high entangled states, and in this case, electron spin can fractionalize. So the elementary spin diffusion freedom is a spin flip, which carries spin 1 in a spin 1/2 system. However, you can have a situation where the ground state is superposition of singlet, a liquid singlet, and in this case, you can have an isolated spin 1/2 fractionalized station. This is called a spin up. And another platform for fractionalization is topological superconductors. And for example, in the two-dimensional P plus IP superconductor, chiral topological superconductor. In this case, again, electrons can form two pairs, but you can have isolated quasi-particles. However, in the presence of vortices, two vortices, they carry these so-called zero-energy modes, known as Majorana modes. And in this case, a single quasi-particle can fractionalize into a pair of spatially separate Majorana modes. So in other words, Majorana modes can be thought as half of a fermion. So basically, we see that there are various types of quantum number fractionalization in the insulating states. With U1 symmetry, the charge can be fractionalized. In spin systems, the spin quantum number SZ can be fractionalized, and even in systems with all proton symmetries, and then the fermionic nature of quasi-particles can further be fractionalized. However, despite all these theoretical interests, for a long time, the fractional Hall effect remains the only system where fractionalization has been experimentally demonstrated. And the remarkable thing is that the fractional quantum Hall effect only relies on the high magnetic field, and it really occurs in a universal way in various material platforms, two-dimensional semiconductors, silicon, gallium arsenide, nickel oxide, quantum wells, as well as atomic distinct layers, graphene and constant silicon, these conventional metal lines. So the physics is really independent of material details, but it crucially relies on strong magnetic field. So many experiments are carried out in the National Magnetic Lab in the field. And then starting from 2 years ago, in 2023, this monopoly of high field fractional quantum Hall effect was broken. And it was found that in some interesting two-dimensional materials, foreign materials, the same kind of quantization of the Hall effect occurs at zero magnetic field. And for this reason, it's called fractional quantum Hall effect. And this was found in twisted MOT2, and also in the same year was found in replicator graphene HBN lattice. And we have experimental experts here who are involved in the discovery of this phenomena. And then in particular, Liang Fu, when we talk about this replicator graphene system, and there's a lot of direct questions. I'm going to focus on this twisted semiconductor system, which is much better already understood at this point. And in fact, as we will show that the theoretical proposals for this platform has been around for some time, and helped establishing this effect. Okay, so so the idea is really very simple. That we know that the fractional quantum Hall effect occurs in the present magnetic field. So how can we achieve the same quantization without external field? The idea is that certain materials it can support some emergent magnetic field. And what I mean by this is that at the quantum mechanical level, the effective magnetic field, the real magnetic field on the charged particle, really enters through the around bond phase. If the particle move around a flux, it picks up a phase factor, which is given by the line integral of the vector potential. Okay. Now, in other quantum systems without external magnetic field, then this role of the Hadron bond phase can be replaced by the Barry phase. So suppose that the quantum state of electron, for example, here I'm representing a two-level system with a spin, and imagine that the quantum state of the system is spatially varied, so which is characterized by this direction of the spin is spatially non-uniform, it points in various directions. And in this case, then the motion of an electron can pick up a Barry phase, which is given by the so-called Barry connection integrated over the electron trajectory. So this Barry connection is the analog of the vector potential. And the phase that it pick up is called the Barry phase. So this idea has been around for quite some time, and in particular, in magnetic materials where electrons spin from a non-coplanar configuration, and for example, is this so-called fermion lattice. It has been theoretically shown 2 decades ago that one can actually perform a mathematically rigorous mapping. Okay, so when the exchange coupling is large, so when electrons spin, rigidly follows the texture of the magnetic moments. And in this case, then this Hamiltonian shown here can be mathematically rigorously transformed into a new one, which is a spinless particle because electrons spin rigidly attached to the magnetic texture anyway. So the active degree of freedom, the low energy Hamiltonian, in the end, maps to a spinless particle moving in an emergent magnetic field together with a potential. And the emergent magnetic field, which is the curl of this emergent vector potential, is directly related to the spin capacity. Okay. And while the emergent potential is related to the spin stiffness, gradient of spin in real space. And in particular, if we have one fermion, then the flux carried by this fermion is 1 plus quanta. And this immediately says that in a metallic magnet with a non-coplanar spin texture, we generally expect a Hall effect, just like a real magnetic field applied to a metal. Now, this effect is called topological effect. It's usually a small correction to the dominating conventional Hall effect as well as the anomalous Hall effect in the ferromagnet. However, theorists speculated that perhaps this was work from more than 2 years ago. But in a low electron density system, okay, if the electron density is comparable to the skyrmion density, and in this case, from this mapping, we will say that the fitting factor, okay, the emergent lambda level fitting factor is only order 1, then maybe this topological Hall effect can be quantized. So this leads to a theoretical proposal of an integer quantum Hall effect from this magnetic spin texture. And this effect, to my knowledge, has not been seen. And also, the same author also pointed out in the same paper that even though the integer quantum Hall effect could be theoretically speculated, the resulting bands are not the same as the levels. In particular, they're not flat. Okay, and that's because the emergent magnetic field is not perfectly uniform. Okay, so we played with this idea in 2021. Worked with my student Shaga Paul as well as Yang Zhang. So we considered some semiconductor magnetic heterostructure, and this Yang's DFT calculation shows that this exchange coupling can be 14 millielectron volt, can be substantially high. And then in this adiabatic limit, we looked at different spin textures that's parameterized by the, several parameters, and in particular, one of the parameters corresponds to the net magnetization, which can be controlled by the Zeeman field, external Zeeman field. And for example, at high Zeeman field, the skyrmion size shrinks. Most of the spins are pointing up. Only in the core of the skyrmion spin is pointing down. And we find that interestingly, these bands, due to the presence of the skyrmion lattice, not only carries the Chen number as you expect for longer levels, but also they can be extremely flat. Okay. So in this case, then the flat Chen bands can actually behave very similar to a longer level, and this may give rise to even fractional quantum Hall effect based on the skyrmion idea. And we hope the experiments will still be interested in this platform. And on the other hand, the skyrmion lattice idea takes another form in twisted transition metal fractionalized. So these materials are nominally non-magnetic. Okay, and in the seminal pioneering work by Alan McDonald and Fengchen Wu and collaborators, they pointed out that even though this system does not have any magnetic elements, secretly the band structure has a resemblance to these skyrmion lattice. So in these semiconductor TMDs, the valence bands are just parabolic bands, and with a spin value locking, the spin up states are in value k, spin down states in value k prime. That's due to strong atomic spin coupling. So at the single particle level, the two values are decoupled. So I'll just focus on one value, the spin up states, for example. And in this case, because of when you take 2 layers of these TMDs and introduce an angle twist, then in this moire superlattice, it consists of different regions: the MM region where the metal atoms are aligned, the XM region where the metal and Chagallon atoms are aligned, and MX region. So because of this spatial variation of the local environment, the electrons actually experience a moire potential on the 2 layers, V1 and V2. And also there's interlayer tunneling between the 2 layers, which is off diagonal. And then this Hamiltonian can be precisely written in terms of this pseudo spin. But the pseudo spin now is referring to the layer index, the top and bottom layer. And these also showed, I'm not going into the details, that this pseudo spin texture actually has a spatial periodicity of the moire lattice, and it actually forms a non-trivial texture, okay, similar to a skyrmion lattice. And for that reason, this kind of texture is expected to produce an emergent magnetic field. However, let's now come back to the spin degrees of freedom. There are 2 values with opposite spins. So the emergent magnetic field that's created is equal and opposite for spin up and spin down. After all, the system is time resolving invariant. Okay. And the net result is that you get a pair, the time reverse pair of spin up and down Chen bands, similar to the K-Malin model. So that's why these authors suggest that at the fitting of 2 particles per unit cell, you can get a quantum spin Hall state. Okay, and we'll hear about it later from the experimental group. So we took this idea further. We asked question, what happens if you have fractional filling? Fractional filling. And at that time, there were some initial experiments from the Columbia group on twisted WSE2 at the 5 degree. And this system shows no sign at all of any non-spot effect. However, I spent a lot of time trying to convince them that if we go to small twist angles, then the effect of strong interaction together with narrow bandwidth may actually produce the non-spot fractional non-spot effect. So, we started to do actually theoretical calculations. So this is using the large-scale DFT calculation. So we calculated the moire band structure, and from that we extracted this continuum model parameters. And these are the band structure at a small twist angle. For example, at 1.43 degrees for twist WSE2. And you see in this case, the topmost valence bands not only carries a Chen number, but it's also extremely flat, almost perfectly flat. And here I'm plotting the blue line plots the bandwidth as a function of twist angle. At small twist angles, the bandwidth is very small, and at a matching angle, it becomes perfectly flat. So when you have these pairs of flat Chen bands, one for each spin, then at a partial filling, then a strong pulling interaction can drive all the electrons spontaneously into one spin species. So this basically is a flat band ferromagneticism. And we show that indeed, by exact dilation calculation with Valentin Krepel, we show that the Magnon gap as a function of the filling factor in the y-axis and the twist angle on the x-axis. And you see in a certain range of twist angles, ferromagnetism exists not only at half filling, n equal 1, but over a wide range, filling factor range, when a single band is partially filled. So this provides a root to the fractional Coulomb effect. In the same way that fractional filling of another level can give rise to fractional Coulomb effect, here fractional filling of a Chen band, of a spontaneously spin polarized Chen band, can give rise to fractional Coulomb non-spot effect. Okay, so this kind of a state is also known as a fractional training series because it occurs in Chen band. And we're not the only one. There's also independent parallel work from Kaishun and Shizhen Ling's group. And this is situation from 2021. And so experiments came 3 years later. So this work from Van Velden's group showed that in twist WSE2, the compressibility measurement measures the gap as a function of amplitude and density. You see these square lines. So these lines tell you the training states down to 0 by amplitude at a factor of 1. And this only occurs at a very small twist angle around 1.2 degrees, very close to the magic angle we identified directly. But
just explain what the picture was actually showing.
Yeah, so the one on the left. The one on the left is the color represents the compressibility.
It's very noisy.
So the color represents compressibility.
On linear scale or?
This is shown here.
Okay.
Compressibility. And when you see these bright lines, this means an incompressible state. The idea is that the density at which the incompressible states occur depends on the magnetic field, and this slope actually determines the Chen number. So from this slope, you infer that the Chen number is 1. And here what's shown is the gap at 0 magnetic field as a function of the twist angle. So these are local compressibility measurements. One can scan different regions of the device, and the different regions have different twist angles. So you see this Chinese training states only occurs at a very small twist angle range, close to the magic angle. Yeah. And but then the real breakthrough came from the study of the twisted MOT2, and was by Xia Dongxu's group at the UW. These are the transport data showing that the RXY shows these 4 plateaus at 0 magnetic field, and these plateaus are accompanied by a dip in RXX, very much like the fractional Coulomb effect in other levels. And these transport studies follow earlier optical studies from both UW group and the Cornell group, which we may hear later. Okay. And also, this is the figure on the left shows the magnetic circular dichroism as a function of the filling factor. Again, you see at the 0 field, the system is spontaneous with ferromagnet over a wide range of Filling factors from 1 all the way to 1/2. So that's consistent with spontaneous ferromagnetism that is needed to get the fractional time zero. Okay, so then inspired by these experiments, we further performed various numerical studies. I trying to understand these systems better. And I'm going to show a lot of the studies. We're using a band project examination. So we take the single particle band structure calculated by either large scale BFT or continuum model, and we project the Coulomb induction into the lowest band. Lowest band is partially filled. Okay. So this is justified when there's a big gap between the lowest band and the higher bands. And for example, at both 1/3 and 2/3 filling at 2 degrees, examination study shows 3 degenerate ground states, and they permute among themselves when you square the flux. So this is the expected signature of fractional Hall states. Okay. So on the other hand, turns out this is far from the full story. When we look at a different angle, 2.5 degree. Okay, in this case, our examination shows that at 2/3 filling, the ground state is still a fractional strain considered. But at 1/3 filling, you see the ground states lie at a different momentum sector. This is in fact the charge density wave states. So that is a prediction. And then we talked to experimental groups, and the Cornell groups told us that indeed, actually, this is the MOT2. I don't know if it's still published or not, but they generously share with us. So at filling factor, you see 1/3 and 2/3. You see a big contrast in the compressibility. At 2/3, you see this line with a finite slope corresponding to the number of 2/3. On the other hand, at 1/3 filling, you see this line is vertical, meaning that the manipulation number is 0. And that's consistent with CW. Yes.
What is the line of the magnetic field?
So this is the color represents.
No, what is the direction of the magnetic field?
What
Is
is
it
the-
Zeeman magnetic field?
No,
or is
it's
it
orbital effect.
orbital magnetic
Orbital
field?
effect.
Okay.
Yeah, yes, good question. Yeah. Orbital effect. So this again, so this case indeed shows that not everything is FCI. Even in the same system at different twist angles, and even in the same twist angle at different filling factors, there are different kinds of states, those are the FCIs and charge density waves. And obviously, this is not something you expect for a lumbar level. Okay? And from this, we learned that the Chen band, even though I keep making an analogy between the Chen band and lumbar levels, its mapping is not perfect. The Chen band does not map perfect to lumbar levels. It actually makes the physics even richer. And indeed, based on extensive examination studies, we established the following phase diagram. The behavior of twisted MOT2 really depends on twist angle. Near a metric angle with around 2 degrees, we find that this mapping to lumbar level is really very, very good. And you see that at various filling fractions, we get all kinds of fractional Hall states, and the behavior is just like at the lowest level. On the other hand, at higher twist angles, most of the experimental studies so far have been on the larger angle. And in this case, the behavior is different. While the 2/3 state is a strong FCI, 1/3 we get a charge density wave. And moreover, between filling factor 2/3 and 1, we found that our ground state is actually a fermi liquid because of band dispersion. Okay. So in other words, there's a strong competing states present.
When you say the ground state's a Fermi liquid, you believe it doesn't have any residual tendency towards superconductivity?
That's a great question. We cannot tell from finite size EV study. Yeah, that's a good question. Now, even in terms of the fractional transfer, suppose we are not interested in competing states. Even in terms of the fractional transfer, we realize there is something new to it, and this is some unpublished result. So as you know that in the fractional quantum Hall effect in lumbar levels, there are these low energy collective modes. That's called magneto-roton. And the magneto-roton has a minimum and a finite wave vector Q, and that reflects the short range crystalline order in the fractional quantum Hall liquid. And however, these collective modes already merged into the particle continuum at a small wave vector. Okay. And also, if we look, these collective modes cannot couple to light. At Q equals 0, the optical conductivity is completely boring. It's basically 0 at all frequencies except the cyclone frequency omega c. And this is because in the Lambda level, due to the Galilean invariance, the center mass degree of freedom that couple to light do not get involved in electron interaction. Okay, so at the frequency is smaller than the cyclone gap, the optical conductivity is completely 0. Okay. On the other hand, as we see that when we map the Chen band of a Sturmian lattice into a magnetic field problem, the emergent magnetic field is not uniform, but it has a periodicity of the underlying lattice. And in addition, the mapping gives us a periodic scalar potential. So these effects actually reduce the continuous translation symmetry to the discrete lattice translation. So then, to a zeroth order approximation, we can think of these fractional transitors as a fractional quantum Hall liquid in the presence of a symmetry breaking perturbation, in the presence of a periodic potential, in the presence of a periodic magnetic field. And therefore, we expect all these collective modes to be folded back into the lattice Brune zone. And in particular, now you see that the magneto-rotor energy minimum, around the minimum, these states are also folded into the gamma point. And we further showed that these modes are now actively active. Yes.
What is the symmetry of this excitation?
Oh, yeah. So this in this material, it has a 3-fold rotation symmetry as well as a 2-fold.
No, but is it dipole active?
It's active. Yeah, exactly. That's one.
Dipole or quadrupole?
Dipole active. Exactly. That's a key difference. The dipole active. Dipole active. Okay. So and indeed, this is our calculation. Take the simple example of fractional quantum Hall state on a level, introduce a periodic potential that breaks continuous translation symmetry. We find that the conductivity now shows these sharp peaks, and these peaks corresponds to these 2 equals 0 dipole active modes. Dipole active collective modes.
I can't see from here. So the plot on the right is optical conductivity.
Optical conductivity, sigma as a function of this is very okay. And you see that light and circular polarized light, they excite different modes, and they are at a slightly different frequency, and the splitting depends on the amount of the potential. So, in other words, I would like to suggest that these FCIs has an intrinsically new aspect that they couple directly to light, and one can probe these kind of modes using microwave and terahertz frequencies.
So it's basically E-symmetry mode in C3.
Basically,
E-symmetry. Those are E representation.
yeah.
in C3.
No, these are the P plus IP and P minus P are split.
Yes.
Right. So one of them shows up as a peak in sigma plus using bisexual light, and the other
Right.
shows up a different frequency.
This is because he. Okay.
Yeah, because of the how much time do I have? Time is with me, please. All right, okay. Let me just do yeah, I'm busy. I'll stop. Yeah. So again, the analogy with so there's now an active research in various directions, and in particular, there's interest in going towards higher fitting factors, and not only in the lowest band, there's approximate mapping for the lowest on the level, but it turns out at some two-angle range, we believe that the next band can approximately map to the n equal 1 on the level, and this provides an opportunity to search for these non-abelian, more read-like fractional transitors. And since I'm running out of time, let me just skip this. And also, a new surprise was found recently from the Cornell group. They showed that even at the integer fitting factor 3, they found a new states that has 0 Hall conductance, but it shows edge conductance that's consistent with 3/2 spin up states and 3/2 spin down states. In other words, in this state, both spin species are involved. Again, that's something that has no analogy with quantum Hall physics, because spin up, spin down states, they have the opposite numbers. So we recently inspired by this experiment, we recently performed some microscopic model study. We take the example of a pair of lambda levels with equal and opposite magnetic fields, and we ask what is the ground state when the n equal 1 pair of lambda level are half filled. Okay, basically 3 halves plus 3 halves. And in this case, we find that the ground state really depends on the interaction. So when we use the bare Coulomb interaction, both for interaction between the same spins and for same Coulomb interaction for electrons with opposite spins, in this case, we find the ground state is fully polarized, as you probably would expect. But on the other hand, we find as soon as we reduce the short distance repulsion between opposite spins, the system will transition into a completely spin unpolarized state. Okay. And what's shown here is the ground state energy at different spin sectors. And you see that as we reduce the short distance repulsion by a certain amount, by a small amount, the ground state becomes completely unpolarized with total energy equals 0. And moreover, when we look at the energy spectrum of this unpolarized state, we find the ground state degeneracy, which is either 36 or 4. Basically, 36 is square root of 6, 4 is square root of 2. Basically, the examination study tells us that the ground state is consistent with a non-abelian spin Hall integrator that is basically 3 halves plus 3 halves, a product of 2 spin independent states. And however, in spin half field lambda level, there's a particle symmetry. So there are really 2 types of ground states, either Fabbian or anti-Fabbian. And combining both spins that leads to 4 possible states. And the 2 of them, the product of the Fabbian and the conjugate of Fabbian, are time erosion invariant. On the other hand, the product of the Fabbian and the conjugate of anti-Fabbian is time erosion breaking, and it has a somewhat off inductance. And okay, yeah. So in the last 1 minute, let me just briefly advertise. Since this workshop about machine learning, recently with Tony Deng, we performed a neural network study of fractional basis. This is called the fractional quantum Hall effect in the disk geometry. And we found that in this neural network directly solved the many electron Schrodinger equation without any lambda level truncation. So therefore, it can capture the system at strong lambda level mixing. And indeed, we find that as we increase the interaction strength, the neural network energy significantly outperforms the lambda level projected excitation. And we also see a transition from a quantum Hall liquid, fractional quantum Hall liquid, into different states. This state has different total angular momentum, and this new state is consistent with the original molecule. Finally, with D-Law and the team, we also are in the process of using neural network variation Monte Carlo to study these fractional training series twisted TMDs. And here again, I'm comparing the energy from the neural network with that of the band projected excitation. We find that at all interaction strengths, the neural network energy is lower than band projected ED, and this tells us another band mixing is important. And here is the ground state structure factor calculated from neural network, and this behavior is consistent with the fractional Hall liquid. Okay, so since I'm running out of time, then just leave the summary here, and thank you for attention.
Yeah, we have one.
Is there any way that you could introduce mixing between bands in the exact diagonalization via some Schrieffer-Wolff type procedure and compare that to the neural network?
That's a great suggestion. Yeah, we thought a little bit about that. It's a lot of painful work to do, and so we haven't done that. And also, that Schrieffer-Wolff is controlled when the mixing is small, but when mixing is strong, it probably won't work. So, for example, in the case of the fractional quantum Hall case, we know that in order to capture the transition from the fractional quantum Hall to Wiener crystal, as we increase interaction strength, we need to mix many lambda levels. So yeah, that's why I think this neural network has some potential advantage.
Okay, please buy it.
For the optical absorption of the non-photon. So with the electric field, one can tune the topological phase transition.
That's right.
And that would evolve into let's say if we have an FCI to a CDW transition, that would evolve into a soft mode or something.
So there will be soft mode not at Q equals 0. Right? There will be soft mode at
Some folded, you know.
No, because the generalized Wiener crystal still breaks lattice transitions.
Okay,
so it's not at the center.
Right momentum.
Yeah, it's still it's at K point.
Yeah, let's thank Liang for the next talk. Yeah.